Good evening, everybody. Thank you for joining us at the I Heart Pluto Science Speakers Series. My name is Amanda Bosch. I am a planetary scientist at Lowell Observatory and also the Chief Operating Officer. This past Friday was the 92nd anniversary of the discovery of Pluto, which we're celebrating at the I Heart Pluto Festival. You can find more information about this festival by visiting our website, iheartpluto.org. Previous science talks are also available to view at this website or on our YouTube channel. Before we get started, I'd like to thank the Orpheum Theater in Flagstaff for sponsoring tonight's science talk. Our speaker tonight is Taylor Perrone, who's a professor of Earth, Atmospheric, and Planetary Sciences at MIT. He's best known for his work on how rivers shape topography on Earth and other planets. Professor Perrone is a fellow of the American Geophysical Union, a recipient of the James B. McIlwain Medal, and a MacArthur Fellow. He holds a bachelor's degree in Earth and Planetary Sciences and Archaeology from Harvard University, and a PhD in Earth and Planetary Sciences from the University of California at Berkeley. We're very excited to hear from Professor Perrone tonight. Before we get started, however, I'd like to let our viewers know that you can type your questions into the chat box and we will pass them on to the speaker. Welcome, Taylor, and let's go get a tour of Titan.
All right. Well, thank you so much, Amanda. It's wonderful to be here chatting with you on what is a rather chilly evening out here in Boston. And so please beam some warm thoughts towards me from the Southwest. I'm really excited to be chatting with you all tonight on this week when you have celebrated Valentine's Day by giving a little bit of love to Pluto, much deserved. But tonight, I'm going to talk to you about one of my favorite places in the solar system, other than Pluto, which is Saturn's moon, Titan. And along the way, I will tell you why I think it's such a fascinating place, and also highlight a couple of things that Titan has in common with Pluto. And so with that, I'm going to start a presentation because it always helps to use some visuals when we're talking about exciting planetary bodies. And the topic more specifically for tonight is the rivers and seas of Titan, both of which are phenomena that I study in my research group at MIT, and which we have been studying in other places in the solar system, including Mars and Titan. I'm going to start with a little bit of history, beginning with the discovery of Titan. And Titan's a place that has been fascinating to astronomers, planetary scientists for hundreds of years. Christian Huygens discovered Titan in 1655. He was an astronomer who was grinding his own lenses to make his own telescopes and found that Saturn had a massive moon. And in fact, at the time, there were only 4 other moons other than Earth's moon known in the solar system, and those were the 4 Galilean moons of Jupiter. So this was a very early discovery in planetary astronomy. And later discoveries revealed that this massive moon of Saturn had some really mysterious properties. Work by the astronomer Gerard Kuiper in the mid-20th century revealed, using spectra of Titan's atmosphere, that it has a very thick atmosphere that's made partly of methane. And that is the only moon in the solar system we know of that has a thick atmosphere. So even in the mid-20th century, it was already clear that Titan was a really remarkable place, not just for its size, but also because of some of its properties. And so subsequent spacecraft missions prioritized getting a good look at Titan. Pioneer 11 was the first to get a much closer look in 1979. And then in 1980 and 1981, the 2 Voyager spacecraft also got a look at Titan. Voyager 1 actually had its trajectory specifically planned to be able to come close to Titan to observe this really remarkable world, try to learn more about it. And I want to emphasize something about the size of Titan, one of the things that makes it so remarkable. Now, our moon is already pretty large with respect to Earth. So if you take a view like this and a nice full moon in the background, if you were to superimpose Titan over our moon, if Titan were at the same distance from Earth as our moon is, this is what it would look like hovering in the sky. So it really is a very large body. It's bigger than the planet Mercury, and it's in between our moon and the planet Mars in size. So really quite large. And sometimes planetary scientists like to describe Titan as a planet-like moon. And there are a number of reasons for that I hope you'll have a better appreciation for at the end of the presentation tonight. But a couple of the really remarkable things about Titan are, first, that it has an atmosphere that is not trivial. And so I've created a yellow circle or yellow box over here on the left, highlighting a few places in the solar system that have atmospheres, including 3 planets, Venus, Earth, and Mars, 3 of the terrestrial planets, but Titan joins them. Again, the only moon in the solar system to have a substantial atmosphere. And then there's this blue box over here on the right that outlines a few worlds in the solar system that have oceans. Now, Earth, of course, has a water ocean at its surface, but there are several other moons in the solar system that probably have a liquid water layer somewhere in the interior. And planetary scientists refer to these as interior oceans, even though they're not liquid water at the surface like we have on Earth. And so these include Ganymede and Europa, Saturn's moon Enceladus, and also probably Titan. And so Titan and Earth are exceptional bodies among the ones that I'm showing here on the screen that have both a substantial atmosphere and also have a liquid water ocean, either at its surface or in the interior. So these are just a couple of properties of Titan that make it exceptional among the moons in the solar system and even among the other terrestrial planets. So to move forward in time, by the early 1980s, after Pioneer and Voyager spacecraft had given us a somewhat closer look at Titan, we knew a little bit more about it. We knew that the atmosphere is mostly made up of molecular nitrogen, like Earth's atmosphere, but there's about 5% methane in the atmosphere. And remember, that was the observation that Gerard Kuiper made in 1944. We also came to know that Titan was very, very cold. It has a surface temperature of about minus 300 degrees Fahrenheit. And I can tell you that that is cold even by Boston standards, which is saying a lot. So what was the surface like? That remained a mystery because it has such a thick atmosphere and because methane ends up breaking down in the presence of sunlight and creating a lot of other complicated molecules. That makes a haze that surrounds Titan and makes it really difficult to see the surface. And so it has this appearance of an opaque ball with this sort of yellowish orange color. Now, planetary scientists use theory to try to understand what the surface might be like underneath that haze. And one speculation was that given the abundance of methane in the atmosphere and the very cold temperatures and high pressures, which actually make it possible for methane, CH4, and ethane, C2H6, to exist as liquids, they speculated there might actually be a global liquid ocean of methane and ethane all over Titan's surface. Now, I told you a minute ago that there is probably a liquid water layer in the interior of Titan. This was a different prediction. This was a prediction that there might be a liquid layer of hydrocarbons. So literally liquid natural gas and liquid ethane covering the surface. And the exact nature of the surface remained a mystery until very, very recently. So even as recently as the 1990s, the best observations of Titan's surface came from telescope observations from Earth or from orbit around Earth, like the Hubble Space Telescope. And so what you're seeing over here on the right is an animation of varying bright and dark patches on Titan's surface as it's rotating around here in a map that was made by the Hubble telescope looking at Titan in infrared wavelengths, where you can see through that thick haze in the atmosphere a little bit better. And so this heterogeneous surface that had patchy light and dark spots hinted that there might be geological activity on the surface, something to create brightening and darkening in these different locations, and that maybe there was at least partly a solid surface and not a global ocean. The thing that really advanced our knowledge of Titan remarkably was the Cassini-Huygens spacecraft mission. This was launched in 1997. It was a collaboration between NASA and the European Space Agency and the Italian Space Agency. And it consisted of two parts. The Cassini spacecraft is the larger part that you see standing up here on end, over here on the right. You can see it's about the size of a school bus and about the weight of a big car. Here are some people down here for scale. And then this is a computer animated version of it over here on the left. And then there's this shield-shaped Huygens probe, which is attached to the belly of the spacecraft, which you can see right over here as well. And Cassini did not orbit Titan, it orbited around Saturn. It was launched in 1997, took 7 years to get to Saturn because it's a long way away, went into orbit around Saturn in 2004 and made many orbits around Saturn, and made a lot of close flybys past Titan, over 100 flybys. And so we got a good look at Titan on a number of occasions over the course of almost 20 years. So this was a really remarkable spacecraft mission that transformed what we understand about Titan. Now I'm going to take a step sideways and let you know another reason why I personally am very interested in Titan. And I think that will set up my excitement about learning all the things that Cassini-Huygens have revealed. In addition to being a planetary scientist, I'm also an Earth scientist, and I study landscapes on Earth. So my research group and I study rivers and mountains and coasts, and we do field work, we use remote sensing data, we use laboratory measurements, we use computational modeling to try to understand how landscapes, like the ones you see in these two images here, form and change over time. What controls how rivers carve valleys and move sediment down through their channels out to the oceans, and what controls the remarkable shapes that coasts and islands take on. So I'm fascinated by these processes on Earth. And one thing that we do in my group is to extend our research beyond Earth and try to understand how these mechanisms might work under more extreme conditions on other worlds throughout the solar system. And this brings me to a point of minor frustration in addition to the excitement. And let me explain why that is. If you're a geologist or a geophysicist and you have a particular process that you like to study, in general, the solar system has got your back. There's an example of a lot of these processes that are happening now in other worlds. So for example, if you're a volcanologist and you like to study volcanoes on Earth and you want a planetary example, well, you can look at Jupiter's moon Io, where there is active volcanism going on. If you are someone who's interested in impact craters, well, you are in luck because you have kind of an embarrassment of riches throughout the solar system. You can look at our moon and many other bodies and study impact formation processes. If you like oceans, I mentioned towards the beginning of the talk that there are a number of worlds in the solar system, especially icy moons around Jupiter and Saturn, that probably have liquid water layers somewhere in their interior. And so there's even a chance to study present-day planetary oceanography, even if you can't see the oceans directly. Now, if you're interested in rivers and coasts, the good news is there are some examples of rivers and coasts elsewhere in the solar system, including really close by Earth. And the best example of those are on Mars. The bad news is on Mars, the rivers and coasts haven't been active for a very long time, billions of years. Now, don't get me wrong, Mars is fantastic. And the evidence of liquid water creating rivers and filling in craters to create lakes and even forming river deltas, like the one you see in this image here, is remarkable. This is an image of Jezreel Crater on Mars, where the Perseverance rover is on its way towards right now. So it's going to be exploring this feature right here, which we think is an ancient alluvial fan or river delta, which was formed by water and sediment that was flowing through this river channel, through the edge of an impact crater. This is the rim of the crater right here, depositing its sediments in what used to be a big water-filled crater lake. So this is a really remarkable view of water-driven activity on a planetary landscape. The catch is that this probably happened billions of years ago. And so you see all this amazing evidence on Mars, but you can't see the processes that we're interested in going on right now. It's almost like looking at a ghost town somewhere in the Western US and trying to tell the whole story of what happened there during the gold rush, even though it's totally derelict now. It's fun, but it can be a big challenge. So one of the reasons that I'm really excited about Titan is that we have some of these active processes going on right now. And what I'm going to show you next is one of the first and most exciting revelations from the Cassini Spacecraft mission. Remember that little Heightens probe with its golden half dome that was on the belly of the Cassini spacecraft that I showed you a few images ago? Well, on one of the first orbits that Cassini made around Saturn, where it flew by Titan, it released the Huygens probe down through Titan's atmosphere, where it passed into the atmosphere and parachuted down to the surface. So I'm going to show you an animation that was put together from images taken by the Huygens probe as it was descending towards Titan's surface. So this was happening in January of 2005. And it was really the first close-up view we got of Titan's surface. And what was one of the first things we saw? Well, networks of rivers carving the surface, flowing downslope into a flat area, which is right where the Huygens probe happened to land. Now, these are networks that are not carved by liquid water into rock like on Earth, but because of the temperature, very low temperatures, and the high methane content of Titan's atmosphere, planetary scientists are pretty certain that Titan has a methane cycle that's remarkably similar to Earth's water cycle, where there are clouds, rain, runoff, and even rivers of liquid methane. And as the probe...
oh, sorry, could I just interject here? We had a question about that methane cycle, if I could.
Yes. Go ahead.
Glenn was asking and wondering about the temperature for when methane would freeze, and if that would mean that the oceans would be, or whatever, methane liquid would be on the surface would actually not be liquid and be frozen.
Yeah, the temperature and pressure conditions are actually not quite what they would need to be to create solid methane. There's a possibility that there might be a sort of a thin skein of solid ethane that forms on the tops of some of the bodies of liquid, but probably not solid methane. So we think that it's mostly in either the gaseous phase or liquid. So that is a bit different from Earth's hydrologic cycle. It's a great question. So as the Huygens probe settled down on the surface, it landed in the midst of what you might call a bunch of rocks. Now, these rocks are probably made of a combination of water ice, which at Titan's surface temperatures is very, very hard, about as hard as rocks are on Earth's surface, a combination of water ice and organics. Now, when I say organics, I don't mean life. I mean molecules that are made up of carbon, hydrogen, nitrogen, so forth. And I'm showing you over here on the left for scale, about the size of these sediment cobbles. They're about the size of a tennis ball, a few inches across. They're also slightly rounded, which has led some geologists to speculate that they may have been moved by rivers on Titan and had their corners rounded off as they moved downslope. So this was a remarkable discovery. The one place that we happened to drop a probe onto the surface of Titan after a very long journey and after decades of wondering what the surface might be like, not even knowing necessarily whether it was going to be a liquid ocean or solid. In fact, the Heightens probe was actually designed so that it would float when it landed on the surface, just in case it happened to touch down in a lake or an ocean. But the one place we happened to land, we saw river networks carved by liquid methane into a surface of water ice and organic material, which leads us to think that that is probably a very common occurrence on the surface. Now, if we zoom out to a much larger view, what you're looking at here is the same map from the Hubble Space Telescope of Titan's surface that I showed you earlier, but it's been unwrapped from the globe. This is the one that was spinning around in animation. It's been unwrapped into a map where north is up, south is down, west is to the left, east is to the right. And if I replace this map, which was before the Cassini spacecraft got to Titan, with a map of all of the images that the Cassini spacecraft collected, we have a much more detailed view of the surface now. Now, what you're looking at here is a mosaic made up, it's almost like a paper mache over Titan's surface, where you see all of these long strips. It almost looks like somebody has put bandages over the surface of Titan. And the reason why all the pictures look like that is that the Cassini spacecraft was flying past Titan, getting closer, making its closest approach, and then getting farther and farther away. So if you look closely, you can see that a lot of these strips are wider at the ends, and then they get narrower, higher resolution towards the center, and then they widen out again. So each of these Band-Aid-like strips was a flyby of Titan's surface. All of these images were actually collected by a radar instrument. So these are not visible light pictures. Radar was very important for Cassini to use because it has a longer wavelength that can penetrate through the thick haze in the atmosphere and see the surface. Whereas if you were trying to use, say, something like a digital camera on your phone that looks at visible light, you would not be able to make a good map of Titan's surface. So we see lots and lots of detail on Titan's surface that we could never see before, and I'm now going to show you more of that. To sum up what we know about Titan's surface in just one picture and a few words, thanks to the Cassini and Heightens mission, we know that Titan has a quote-unquote geologically young surface that doesn't have many impact craters. There are only a few dozen craters that have been identified over Titan's surface. And that suggests that the surface has been renewed somehow through geological processes. It's not just a 4 billion-year-old surface that's been collecting impact craters for that entire time. Now, when I say young, young to a planetary scientist who looks at these surfaces means somewhere between 100 million and a billion years old. So it's not exactly young like Earth's surface, but it's nowhere near as old as, say, Mars's heavily cratered southern highlands, or even the anorthosite highlands of the moon. We also know that there are methane clouds and rain. So there is weather at present on Titan that's creating all of these interesting surface features. Methane rivers have eroded into the icy crust, and you can see a few more examples of these networks, branching rivers that flowed across Titan's surface, carved into the ice all over the image here. And many of them, at least in the North Polar region that I'm showing you here, flow downslope and they end in these large liquid seas of liquid methane and ethane. So we see active processes that are shaping Titan's surface now, which to someone like me who studies rivers and coasts was extremely exciting to see. Mars is fantastic, and we can see Mars in a lot more detail than Titan. But on Titan, all of this is happening now. So even though we have a slightly fuzzier view of Titan, and it's a lot farther away and therefore harder to send missions to, the processes are active now. Now, given all of these amazing discoveries, it's attracted a lot of interest, not just from scientists, but even Hollywood has its take on Titan. And so if you search Netflix, you can find The Titan, in which Sam Worthington is trying to help humanity escape an Earth that has become intolerable. And the way we've decided to do this is by genetically engineering humans to be able to survive in Titan's atmosphere and even to swim in cryogenic liquid methane. And so what you can see up here on the right is all of the trainees training to survive in a pool of super cool liquid methane. And well, I won't give you a spoiler of what happens down here in the lower right, but suffice to say that it is a very interesting take on surface processes on Titan. Now, is it unmissable, as the quote here suggests? I'm not so sure. If you want to devote an hour and a half of your life to it, you can be the judge. But I'm not exactly giving you a ringing endorsement, but a very interesting take on active surface processes driven by a methane hydrologic cycle on Titan. Okay, so that's what Hollywood thinks. What do we actually know as far as the science goes for Titan's rivers and seas? I'm going to tell you a little bit about what we've learned, including through research that my group has done about the rivers, and then we'll move on and talk about the coasts. So I'm starting here with an image of some of Titan's rivers draining into one of the seas in the North Polar region. And now I'm going to zoom way into near where the Heightens probe landed and ask, well, how do we actually know these are rivers in the first place? What we see mostly are dark paths going across the landscape in these images. So this little red dot right over here is where the Heightens probe touched down. And I've drawn a white rectangle here around some of these river networks that I've given you a zoomed in view of right here. It has an irregular outline because it's composed of a few images that were overlapped with one another to create a bigger view. Well, we know they're rivers for a few reasons. First of all, they don't cross each other. They tend to start near locations where other rivers start, which suggests that they are originating near the tops of ridgelines. In general, the larger an area that is drained by these networks, the wider the dark path is that we see in the images across the surface. And that's consistent with what we know about Earth's rivers because, well, we know water flows downhill. It starts near water divides, it runs down slope, and as it collects into smaller rivulets, bigger rivers, streams, the larger the area that's collecting rainfall upstream, the larger the river, the wider the channel, the bigger the valley it can carve. And we see similar things happening here on Titan. Even beyond those characteristics, we also have a little bit of topography thanks to stereo imagery. So if you've ever seen one of these images where you put on the goggles and one eye has a blue foil and the other one has a red foil, and you have two pictures that are offset by a little bit that help you see stereoscopically like your eyes do. The Heightens team was able to do that with images collected by the Heightens probe and make a digital model of elevation in this elevated area that these rivers are flowing down. And that tells us that they are indeed going from areas of high elevation, like here in the red, downslope to lower elevations like the yellows and greens. And we know that these dark streaks across the image, these networks that look like tributaries, are in fact in valleys. So they're actually in topographic lows, valleys that have been carved by these channels. So we have pretty good reason to believe that these are river channels that were carved by methane rainfall flowing over the surface and collecting into organized flows, even though we can't actually see the rain happening directly. So what can we learn about Titan's surface by studying rivers on Earth and trying to transfer that knowledge to Titan? That's one of the things we try to do in my group. And one thing we've done is use measurements of rivers on Titan that we can make from some of these radar images that I've been showing you, like measuring the length and the width of a river channel like Saraswati Flumen here on Titan, measuring how steeply it slopes as it travels across the landscape, and use relationships from Earth, scaling appropriately for the differences in gravity and the differences in the properties of the liquid methane instead of water. And we've been able to calculate the rate at which liquid flows through some of these channels. And for one of the biggest ones we see on Titan, Saraswati Flumen, which flows into Ontario Lacus, which is a lake in the southern hemisphere that I'll show you in just a moment, we've calculated the rate of flow of liquid methane maybe up to about 1 million cubic feet per second. Now, that's a really big number, but how big is that? For comparison, that is about the level of the annual high flood in the Mississippi River. Now, when you consider the fact that Titan is in between our moon and Mars in size, so quite a bit smaller than Earth, that's a pretty big flow. And we've done this for other rivers in a few other locations elsewhere on Titan's surface to be able to estimate what the rates of flow are. Another big question about Titan's surface environment is, how hard does it rain? If we can't see this liquid methane rain happening directly, meaning we can't actually observe the drops falling through the air, we don't have a rain gauge on Titan to measure how fast it falls, can we use the rivers there to be able to estimate what a Titan rainstorm is like? Now on Earth, we can do something like this by taking advantage of the connection between a river's watershed, its flow, and the sediment that it carries. So in a river like the one we see on the right here in Alaska, you can see how rain falling on the landscape or snow melting off the landscape, the water would flow down this side of the valley, down the other side of the valley, away from the water divides, and into the river channel here. And you can also see that this river is moving sediment, gravel and sand, that it's eroded out of the rock upstream. And we know that to erode this valley, the river must be strong enough. It must have enough flow to be able to move the gravel and sand that fill in its channel. And so we did a calculation on Titan where we took these tennis ball sized rocks. I should call them sediment cobbles. It's technically not rock. We took these tennis ball sized sediment cobbles on Titan and measurements of the river channels around the Heightens landing site. And we calculated how hard it would have to rain on Titan to be able to move sediment cobbles of that size to be able to carve these valleys. And the answer we got is that rainfall on Titan could be as much as about 1/2 inch per hour, which is similar to big storms that we might experience on Earth. So the rainfall rates on Titan, we think, at least in some locations, are probably Earth-like and can be fairly intense, although we don't exactly know how often they happen or how long they last. Now I'm going to move into the last part of my talk and share with you a bit about what we've learned about Titan's lakes and seas, which were another hugely exciting discovery that were revealed almost as soon as the Cassini spacecraft got to Saturn and started to fly past Titan. So I'm showing you a couple of views here that are looking down at the poles of Titan. Just to orient you, I'm going to put up a couple of maps of Earth. If you were to look at this kind of map projection on Earth, this is what it would look like. Over on the left, you're looking down at the North Pole, and so you can see Greenland, North America, Eurasia. And over here, you're looking straight down at the South Pole. Or if you like, if you're a Northern Hemisphere occupant like me, you're looking up at the South Pole. Here's Antarctica, southern tip of South America, Africa, Australia. Okay, so to go back to Titan, we're looking straight down at the North Pole on the left, the South Pole on the right. And what you can see is that in the North Pole, all of these blues here are the liquids. All of the yellows here is dry land. Now, these are not the true colors of Titan's surface. This isn't what you'd see if you were standing there or taking a picture with a camera. These colors have been accentuated to highlight the difference between the liquid and the solid ground. What you can see is that there is a whole collection of little lakes over here dotting the landscape, and then these larger bodies of liquids, which we call seas, over on another side of the pole. Now, we don't know exactly why there's that difference in the spatial distribution of the lakes. That's something that planetary scientists are actively trying to work out. But one thing that's very striking about this is you can see the difference between all of the liquid in the North Polar region, between the lakes and the seas, versus the South. And if you look in the South Pole, the only large lake is Ontario here, this little kidney bean shaped one right down here. So one of the striking things about the lakes and seas on Titan is how asymmetrically distributed they are geographically. They're almost all in the North Polar region. And I'll come back to why that might be in just a couple of minutes. Another remarkable thing about the lakes and seas on Titan is how big they are, not just compared to the size of Titan, but in an absolute sense. And so here, Sam Birch from MIT and colleagues from Cornell have put together a fantastic graphic that's comparing some of the biggest lakes on Earth, starting with the Caspian Sea and going all the way down to Lake Winnipeg here. All the blue ones are large lakes on Earth. And then all of these orange-brown ones are lakes and seas on Titan. And you can see that Titan's biggest lakes and Earth's biggest lakes are about the same size, which is pretty remarkable. So relative to Titan's size, that's especially impressive because it's so much smaller than Earth. So there's a huge amount of liquid on Titan's surface that's stored in these lakes and seas. And we're able to make an estimate of how much volume is there in some of the lakes and seas because unlike water on Earth, radar, which the Cassini spacecraft had, is able to penetrate through liquid hydrocarbons up to a few hundred meters. And so there are maps of a few of the seas and lakes like Ligeia Mare here on the left and Ontario here on the right. And what you're seeing here in these colors is just an indication of the depth of the liquid. So these bright blues are the deepest liquid, and then over here near the coasts, these reds and browns are the shallows. And you can see that Ligeia Mare gets up to about 200 meters deep at the center, and Ontario gets up to almost 100 meters deep. So several hundred feet. One thing we don't know for sure yet about Titan is what the surfaces of these lakes are like, and if there are waves that modify the coastlines of Titan. And this is a topic that my research group is actively working on, trying to understand if waves on Titan's lakes are actively shaping its coast. We know there are probably tides on Titan, but waves is still a question mark. So the surf report for Titan is currently also a question mark. Even if there are waves there, they may also be too small to surf. So Sam Worthington from Hollywood shouldn't get his hopes up just yet about surfing there. But there are some interesting clues that suggest there may indeed be waves. Here's Ontario This is the kidney bean shaped one in the South Polar region. When I enlarge it here, it looks a little bit more like a footprint. And you can see that the coast over here on the right is very smooth and resembles wave-smoothed and wave-formed beaches that we see on Earth. And so one thing that my group is working on is trying to quantify the relationship between coastline shape and wind direction from Titan climate models, and trying to understand whether some of these coastlines that are smooth might be the product of wind-generated waves. My colleague Jason Soderblom at MIT also has identified hints that there may be light scattered by waves, glints off of the surfaces of some of the seas, like this one right here, that may be evidence of a wavy surface. So there's tantalizing evidence from Cassini that there might be waves on Titan seas, but we're going to have to do a bit more research to try to see if we can find other evidence in the shapes of the coasts there to tell us whether there are in fact active waves generated by wind. Now, where there are seas, another interesting question is whether there is sea level change. This is something that we certainly experience on Earth. And one reason we've experienced lots of sea level change in the last few millions of years on Earth is because we've had repeated ice ages. And the reason we've had repeated ice ages is in part because of changes in the distribution of sunlight reaching the Earth as Earth undergoes subtle variations in its orbit around the sun. And this has happened dozens of times over the last few million years. And that has caused Earth's sea level to change by hundreds of feet, about every 100,000 years or so, going back further in the past, every few tens of thousands of years. So does something similar happen on Titan? Well, there aren't any glaciers on Titan that we know of. So there probably isn't sea level change due to a mechanism that's very, very similar to what we had on Earth. But it is possible that sea level changes on Titan in a cycle that's somewhat analogous to what we've experienced on Earth. And planetary scientists have suggested that that may be the reason why there's this very asymmetric distribution of liquids, with most of the liquid methane and ethane in the North Polar region and very little in the South Polar region. And the suggestion is that subtle variations in Saturn's orbit around the sun, and because Titan orbits Saturn, kind of like our moon orbits Earth, where the same side of Titan always faces Saturn. We say that it's tidally locked around Saturn. These variations in Saturn's orbit also influence the distribution of sunlight that Titan gets at different latitudes. And so one hypothesis is that Saturn and Titan are currently in an orbital configuration that causes most of these liquids to migrate via the hydrologic cycle to the North Polar region. So maybe we're experiencing very high sea level currently in the north and low sea level in the south. But the suggestion is that every few tens of thousands of years, that's going to reverse, and we might actually see abundant liquid in the south. Unfortunately, we're not able to wait that long to see whether this actually occurs, but there's other geologic evidence that there may have been more extensive seas in the south in the past. The final thought that I'll leave you with about rivers and coasts on Titan is that there are a lot of interesting things that can happen where rivers meet the coast. On Earth, it's a location where liquids mix together. So you have fresh water from rivers mixing with salt water in the oceans. You have sediment that's being delivered to oceans. That creates an exciting environment for life and ocean chemistry. It's also an interesting place to look because rivers erode rock and collect sediment from a very large area and concentrate it in a very small area when they form a river delta. And this is one reason why we are currently exploring a river delta on Mars, because it has already sampled a large area of Mars's surface and put all that material in a place where we're pretty sure there was liquid water in the past. There's at least one place on Titan where there appears to be a presently active river delta, and that is in Ontario Lacus. This is Saraswati Flumen, the river that I showed you earlier that may have a flow rate as high as the Mississippi on Earth. And we think that these two little rabbit ear shaped lobes are two lobes of a river delta, almost like the different lobes you see of the Mississippi Delta here. It's curious, though, that there don't appear to be lots of river deltas in other locations on Titan. And we think that may be in part because most of the liquid is in the north, where sea level has been rising. And that sea level rise may have been fast enough to be able to drown any deltas before the rivers could build them out into beyond the coast. Whereas at Ontario Lacus in the south, the sea level may be near its minimum. And so the river that's building this delta here hasn't had to keep up with sea level rise.
There's a question here from Laurel. If you could, go back to that one. Sure. Thank you. Wondering what the black regions are on these maps. And I'm guessing that maybe she means on Ontario Lacus there and on that little map of Titan in the corner that
like
you
over
have.
Here. So thanks for the question. This black area here is Ontario Lacus itself. So this is the coast, and this is darker because the hydrocarbon liquids absorb more of the radar, whereas the icy and organic surface scatters more of the radar. And then over here on the right, once again, you're looking down at the south pole of Titan. So here's Ontario Lacus there, and that's that dark spot right there.
since we're here, if I can just ask you on the image you have of the Mississippi, what's the green represent?
Oh, that's also a great question. So this is an enhanced color image from a satellite. So this is not exactly what you would see in true color if you were looking from space at the Mississippi Delta. It's been enhanced to show areas where there's sediment deposition going on and where there's vegetation growing. And then some of these milky blues here show different depths of water. And then you can also see in these sort of bright or faint tan colors where there's sediment that's accumulating at shallower depths. And in the middle, the colors on the image of Mars are showing different compositions of the surface. So abundances of different minerals in the rocks at the surface.
Okay, great. We had a talk earlier this week from Kelsey Moore about the Mars 2020 and Jezreel Crater as well. So we got to learn a little bit about that.
Well, I'm sure you heard all about the place that I've been showing you a couple of times in these slides. That's fantastic. Good.
Thank you.
So let me wrap up then by just saying again that I think that there are a number of reasons why Titan can be considered a somewhat planet-like moon, which has characteristics that other moons in the solar system don't have, and which make it a geologically active moon and a very exciting place to study. I also want to note here one of the ways in which Titan is similar to Pluto, and that goes all the way back to the beginning of the talk when I was talking about its discovery, and by Heightens. And up until around 1980, it was actually thought to be the largest moon in the solar system. It was known to be the largest moon of Saturn, and it was thought to be larger than any of the Galilean moons of Jupiter. It turns out that that was partly because its atmosphere is so large. And so it gets a little extra poof, almost like, if you're measuring your height, if your hair gives you a little extra height there. But when Voyager got close, it was determined that it actually was a little bit smaller than Ganymede. So Titan got demoted too, from being the largest moon in the solar system to number 2, but it's still really, really special. And I'll just close with a look to the future. We are going back to Titan. The Cassini mission is over. As many of you probably know, the Cassini spacecraft was intentionally crashed into Saturn's atmosphere, but launching in the late 2020s with a scheduled arrival in 2035 is the Dragonfly mission, which, as the image here shows you, is planned to be a drone, a battery-powered drone that is going to land on Titan's surface, not too far away from where the Huygens probe landed, just a bit farther north, and is going to spend some time exploring Titan's surface, looking for, among other things, evidence that the kind of chemistry that Earth might have experienced before life arose could potentially have been going on Titan, even if life never arose there. And I'm hopeful that it may actually see a few rivers as well, because we know from Huygens that there are some around the equator near where Dragonfly is going to land, even if we can't see them directly in the coarser resolution radar images. So it's a very exciting time for exploration of the Saturn system and Titan in particular. And although waiting 7 years for a mission to get from Earth to Saturn is a long time, it's really a blink of an eye relative to the total amount of time that we've been puzzling about Titan for hundreds of years now. So I will close my presentation there. I'm going to take my visuals down, and I hope that I've conveyed to you why I think Titan is a fascinating place. Hopefully, some of you share some of that fascination now, and I would be happy to take some questions. So thank you all very much.
Thank you, Taylor. That really was fascinating. That was a good word for it. We do have some questions that have been stacked up here, so I'm going to just go through some of them. Back on the images that you were showing us of the landing area of the Huygens probe, and you were referring to the settlement cobbles. And so what's their composition? Do we know?
Well, this is a great question. We don't know exactly, but it's likely that they are made primarily of water ice, but that ice may have at least a coating of organic sludge on the surface, and it may have some organic material mixed in with the ice as well. Now, there were instruments on board the Cassini spacecraft that were designed to try to measure the composition of Titan's surface using the characteristics of the light that is reflected back. But it's very difficult to do this when you have mixtures of lots and lots of different materials in a planetary situation, but probably a combination of water ice and organic material. And that's interesting, it turns out, when you're studying the rivers, because water ice and organics in liquid methane is actually more buoyant than sediment made of rock is in water on Earth. So we think that the rivers on Titan just actually have a slightly easier time moving sediment there than they do on Earth.
Oh, that's interesting to think about. Cool. Okay. We have another question here from James. How is the gravity on Titan and the affects how the river flows?
Good question.
Because of that gravity, yeah.
Yeah, so gravity on Titan is 1.35 meters per second. That's the gravitational acceleration. On Earth, of course, it's about 9.8 meters per second, quite a bit smaller than on Earth. And that is one thing that we take into account in doing all of these calculations about the flow rate of rivers. So it turns out that there's kind of a trade-off. On the one hand, because there's less gravity, some of the flows might be a little bit slower on Titan than they would be otherwise on Earth. But of course, it also has other consequences. It also can exert less stress on the bed, or less force on the bed of the river than on Earth. And that can have some implications for how erosional processes might work there. So it is quite a bit less on Titan, just like it's less on Mars, although not quite as small as on Titan. And this is something that we have to try to account for when we take what we know about rivers on Earth and apply it to Titan.
Apply it there. Well, this was actually a question that I had was, do we know the depth of any of these river channels? Would we have anything similar to like the Grand Canyon?
Yeah,
Titan.
We don't have the capability to measure the depths of the rivers. There is evidence from some of the radar soundings of the surface that there is actually liquid in the canyons, which is evidence that the rivers are actively flowing now. But the depth is one thing that we try to calculate. We can measure the slope in a few places, how steep the surface of Titan is, and we can estimate how wide the river is using a combination of radar soundings and then the images the radar collects. And from that, we try to calculate a few other things, including the depth of the flow.
Okay.
Yep.
All right. We have another question here from Stephen. Do we know if there are the equivalent of seasonal variations on Titan?
Oh, yeah, there are seasons on Titan. Absolutely. They are longer than seasons on Earth because Saturn's orbit around the sun, which controls Titan's seasons, takes a long time. It takes about 29 Earth years. And so to go from one Titan summer solstice to the next takes almost 30 Earth years, which is one reason why the Cassini mission wanted to stay around Saturn for so long, so that it could get to see seasonal change occurring on Saturn. When it got there, it was during southern summer, and then it stayed on through the equinox. And so it got to see at least part of a seasonal cycle, though not a complete one. And so with those seasonal changes, you do see differences in where clouds form on Titan's surface. And there's some evidence that there are differences in where rainfall occurs as the seasons change, although that's difficult to observe.
Oh, okay. Okay. Glenn has another question. Is the position of those larger lakes in any way related to the tidal lock of the moon with Saturn?
Is it related to the fact that the moon is tidally locked around Saturn?
I think that's what he means, yeah.
Not that we know of. The main speculation as to why there are small lakes in one part of the North Polar region and large seas in another part is that perhaps the composition or the structure of the surface material is different in those two regions. And so it may be that the little lakes form through a different mechanism than the larger seas do. It's been suggested, for example, that although water ice does not dissolve in liquid methane, there are some other substances that could form solids on Titan's surface, like acetylene, that might be able to dissolve in liquid hydrocarbons. So it's possible that some of those lakes are almost like karst lakes, like you would see in Florida or the Yucatan Peninsula, where you have dissolution of limestone by water. But
Okay.
this is an idea, but we don't know for sure yet.
We'll obviously need some more data. When you mentioned that the surface of Titan is very young, and so we don't see very many craters. Are the craters concentrated in one area on the body?
They don't seem to be focused in a particular area.
Okay.
The last count, I believe there's about 80 identified craters, which is quite a small number, smaller than you would expect given the resolution of the images that we have. And the best guess is that there is some mechanism that erases those craters, either by allowing them to sort of relax and smooth out over time, or by covering them over with another substance, or by eroding them away.
Okay. So one of the things, so for instance, we don't see any lakes on Titan that look like crater lakes.
There are a few little enigmatic round features that fall within the lakes or near the edges of the lakes that some have suggested might be impact craters. It's not clear whether that is true or whether they form through some other mechanism. But I've noticed these myself, and they're quite mysterious. But as for the larger lakes and the seas, it's not obvious that any of them are just filling in craters, although it's possible that some of the lows in elevation could be craters that have just been altered so much that they're difficult to recognize.
Yeah, okay. We have another question here. A question about discovery of auroras on Saturn and if it has anything to do, if it is connected in any way with any of these processes on Titan.
It's a good question. I don't know much about auroras on Saturn, so I'm afraid I can't offer much about that question. But I have not seen anyone invoke interactions with Saturn's magnetic field to explain surface processes.
Okay. Another question from James. Would a robotic boat or submarine type lander be in a future mission plan, perhaps?
I think there was at least one mission concept that someone has proposed of putting a submarine in the seas. There has been a mission concept for floating a boat in the seas, among many others, winged aircraft, lighter than air vehicles like balloons. The fact that you have this thick atmosphere and low gravity creates a lot of, and surface liquid creates a lot of possibilities for moving around the surface and taking measurements. The challenge, of course, always is the engineering risk. And if you're going to invest lots of time and money and people hours in putting a mission together, you want to choose something that is going to let you get around the surface, but is going to be is going to minimize the risk. Now, even a drone, a rotorcraft like the Dragonfly mission certainly has some risk associated with it, but I think holds a lot of promise. But lots of mission concepts like this have been suggested,
and I'm sure will be again in the future because it's just a fascinating place. We have a question from Keith. How can we assure that the lander on Titan would not contaminate it?
Mm. You know, this is a question that NASA and ESA take very, very seriously when planning spacecraft missions. Planetary protection is the phrase that's usually used to describe this. And so ultimately, the answer is we don't know for sure what's there. But typically, the approach is to try to sterilize spacecraft very thoroughly before they leave Earth. And of course, you know, the years that it takes traveling through space is also an opportunity to help with that. Titan is one of those worlds that's considered a place where the kind of chemistry that might eventually have to the development of life may be occurring, but there are some other reasons to think that it may not harbor life now, including the low temperatures and the lack of liquid water.
Indeed, yeah. Okay, I'm going to keep going here. We have a question from Art and Sharon. Do we have any idea what Titan's core materials are? Are they different from materials on the surface?
Yeah, that's a great question. Titan, based on its density, and now based on measurements that Cassini has made, including using the trajectory of Cassini to be able to gauge the gravitational forces exerted by Titan. Titan is probably about half silicate rock, which is what makes up Earth's crust and mantle, and about half ices, probably mostly water ice. So it's thought that there is a core that's made of rock, similar material that makes up Earth's crust. And then outside of that, there are various layers of water ice, and the ones closer to the interior are probably higher pressure phases that have a different crystal structure than some of the ice that's currently outside my window here in Boston. And then there's a liquid layer, this possible ocean layer that may be a mixture of water and ammonia. And then outside of that is the crust of water ice. Ice 1H is the structure of ice that we're familiar with at Earth's surface. So yeah, it probably is differentiated. That's the word we use to describe when a planet or a moon separates into compositionally and distinct layers.
Oh, very good. We have a question from Laurel. Could microbial life exist in the subsurface liquid water ocean?
It could, potentially. And that is part of the reason for interest in a bunch of different places in the solar system, several of which I showed you earlier in the presentation, that probably have liquid water layers inside them. And there are differences among these worlds, differences in composition and size that could give rise to differences in composition and thickness and temperature of the liquid water layers. But this is one reason why scientists are so interested in places like Europa and even Enceladus, which is another moon that I showed you earlier, which has these jets of water vapor leaving its surface, as candidates for places where you could potentially have microbial life living in liquid water. The trick, of course, is figuring out how to measure that and how to get close to it.
Right, absolutely. So I have a question. So Titan's atmosphere right now is quite thick, and so do we have any evidence that if it had been different in the past, less thick, more thick?
This is one of the $1 million questions for Titan scientists. It's a really tough one. One of the puzzles about Titan's atmosphere is that there is so much methane now, enough that if you were to condense all of the methane gas out of the atmosphere into a layer of liquid, you would have a layer that was meters of methane thick. So wow. many feet thick on the surface. But that's surprising, because even though Titans and Saturn are pretty far from the sun, 10 times farther from the sun than Earth is, there's still enough sunlight to be able to break apart the methane in the atmosphere. And once you break it apart, you break apart that CH4, a lot of the hydrogen escapes. And so the methane gets destroyed. That's one way that you make some of these other compounds like ethane and hexane and other hydrocarbons that make up the haze and that probably settle out onto the surface. But it also means that in order to keep the methane around, you have to replenish it somehow. And if you didn't replenish it, the methane would be gone in tens of millions of years, as far as we understand this breakdown process due to the sun. So this has led to speculations that maybe the thick atmosphere could be a recent phenomenon, or at the very least, that it hasn't been exactly this way for all of Titan's history. But we don't know for sure, and this is something that planetary scientists like to discuss with great vigor and sometimes disagreement.
Absolutely. Well, I'm sure that we could continue talking about this forever. We have one final question from Glenn. Besides the camera sensors, did Huygens have any other instruments to gather data? Radar, thermometers, pressure sensors, etc.
Yeah, there were other instruments. It's always a trade-off between what all the things you want to put on a spacecraft and how much power and weight you have space for. But yes, there were other instruments that took a bunch of measurements as it parachuted down through the atmosphere to measure atmospheric pressure, to measure temperature, to measure winds, the composition of the atmosphere. And in fact, when it came down and hit the surface, there was even a little device on the bottom that was designed to measure how strong the surface was when it splatted down. So there were a bunch of other instruments, and I always find the camera arrays to be really impressive, especially considering the fact that they launched in 1997, and they were technology from well before 1997. Well, I don't know about you, but I didn't have a very good digital camera in the early 1990s. So the fact that they were able to collect even this imagery from such a great distance in such a hostile environment is really remarkable.
Absolutely. Absolutely. Really, it's amazing all of the data that we've gotten and all of the work that went into getting it. So, okay, we're going to stop there and just thank you so much for this discussion. Just a really great sharing of information, and we really appreciate it.
I'm always happy to talk about Titan, and I was especially happy to talk with this crew, and was happy to hear the fantastic questions. So thanks very much.
Thank you, and good night, everybody.